Hello, folks. This is Sungtek Kahng, associate with International University from Korea. Uh, in the first place, I congratulate you on having this great event, which gives a very important educational information to students and researchers, and let them hear about what experts from different fields or sectors of the industry from microwave engineering and antennas are working on. So, let me tell you, uh, for the personal reason, I couldn't join you in person, but for the later time, I would like to find my own opportunity to join you for microwave engineering events or antenna related events. Let me get it started. This is the first slide of my presentation material that tells you classic filters and metamaterial filters. I'm going to tap into basic design methods that you already have been familiarized with, but it is important to mention what basic design methods are for the newbies in this field and numerical approaches which assist the basic design methods working more efficiently. And on your left hand side and right hand side, you can see the field uh, distribution of substrate integrated waveguide structure, the one resonator or one cavity structure. On the right hand side, you see um, at a glance, it shows you two cavities, but this consists of two dielectric layers. Underneath of this top surface, there's another pair of cavities. So this is the filter shape of SIW fourth order filter. The filter has the field distribution which goes from resonator one or cavity number one to cavity number four for the specific structure. As you see, the electric field of each of the resonator or cavity looks very healthy. That is one of the effects after designing your antenna exactly or well, then you have a lot of uh, points of view to check your filters are working well or not. I should tell you what I do and who I am. A couple of years ago, I was the general chair of Asia Pacific Conference on Antenna Propagation. My work comprises three big uh, important fields in microwave uh, engineering applications. Components or devices development is my category number one work. Category number two work is antennas. Category number three is applications of numerical analysis or computational electromagnetics. As you see, a gallery of pictures where I actively work on meeting people to introduce what I do and what devices I have developed for them or for the future customers like this. This is one of the pictures taken in last year's satellite show in Washington, D.C. And low Earth orbit and mid Earth orbit consortium people oftentimes visit me to have a discussion on where I can provide them with components or antenna beamforming antenna systems. And a couple of times I was lucky to get awards on my achievement, technical achievement for 5G and 6G um, antennas. And recently I could establish a research institute, which a research center for working on and developing microwave and millimeter wave devices for satellite, as you see, a satellite which replaces the reflector antenna, parabolic reflector antenna, such as the horn array, like that. And I also put the very important stress on high priority on antenna measurement to check how my antenna or components is working. Yeah, this entire uh, collection of pictures tells you uh, filters, as you see, metamaterial based filters and metamaterial based couplers and power dividers for improved performances compared to other um, reported structures or reported development. And the metamaterial based antennas for IoT applications. The last column of pictures tells you the beamforming performances can be generated by my metamaterial based antennas. Um, to summarize what have been displayed here is all are working for size reduction or volume or weight reduction as well as performance improvement. And I all the time check whether my antennas or microwave or millimeter wave components are working as designed or as planned by checking dispersion curve, which oftentimes or most of the times appears in metamaterial field. Yeah, dispersion curve, which tells us where left-handed region and right-handed region occur uh, uh, from the step of design. After this design, simulating that structure in the well-known high precision electromagnetic simulator, we can see the field distribution which shows us zeroth order resonance. Uh, this is a third order filter which consists of three ZOR resonators. Each of these resonators has, independent of the others, zeroth order resonance, and order resonators are coupled together. Entire geometry also becomes a zeroth order resonance. That was me who, for the first time in the field of microwave engineering and millimeter wave engineering, showing this can be implemented. And size reduction is one of the purposes we should adopt metamaterials for antenna and filter designs. As you see, huge and remarkable size reduction is obtained by compare. Sorry, by comparing. Excuse me. Black. Yeah, by comparing my CRLH or composite right and left-handed filter for 120 megahertz, much smaller than that of the edge couple filter for the same frequency. Actually, yeah, this uh, edge couple filter can be designed by using the classic design methods, but for implementing way smaller geometry relying on nonlinear dispersion based and zeroth order resonance based structure requires a different approach. If you are interested in CRLH or metamaterial filter designs, don't hesitate to contact me. Yeah, I would like to share in a playground where we can see each other and exchange our technical interests. There are a bunch of international uh, renowned conferences. One of them is Peers You can prefer IEEE events or conferences, but they also joined uh, this conference annually. This comes to Japan, even though I'm not a citizen of Japan, I was invited to work as a TPC co-chair for this big event. So I highly recommend this conference to you for giving us the progresses in the field of applications of EM areas. This is the agenda. Uh, as you see here, you're getting close to filters. Yeah, the what the start for starters, you will see the roles and the positions of the filters in the communication system, and there will be two different chapters. The first chapter will talk about the classic filter design, which has been already taught in microwave engineering classes or applications of electromagnetics. Another chapter, different from the second chapter, filter design methods with optimization. Uh, what optimization uh, goes really working powerfully with the classic filter design methods. So as far as you master or have a good mastery in classic filter design methods, actually optimizations will make your ways to design filters very smooth or smoother. And the conclusions and appendices will be uh, coming along after the main part of this presentation. Yeah, in the first segment, we want to know what filter does, especially to have good quality of communication, part of the communication system. You will see this. Yeah, uh, every uh, student of microwave engineering 101 or communication theories 101, they see this. Um, if this is a transfer function of a black box is a model of a simple model of a communication system. So input port is the gate where the radio frequency signal is coming in, and output port is the input signal is amplified or filtered uh, as the product of a communication system work. So as you see, the transfer function of that black box or communication system tells you as to one, this is the symbol of the transfer or transmission coefficient of the system from device to modules or subsystems. We are used to using S1. This is a transmission coefficient from port 1 to port 2. Ports 1 and 2 mean input and output ports, respectively. Yeah, go means the passband, and stop uh, is where the unwanted frequencies are suppressed. So when you see the abscissa as the frequency or frequency axis at a certain uh, uh, block is designated as the passband, except that region or segment or block, you say stop bands. And there are four kinds of, uh, in general, four kinds of filters. Yeah, filters, part of the communication system at the bottom of this presentation slide. As you see, bandpass filter, you can see uh, the parts or the segments checked V here. Yeah, bandpass filter, and low pass filter, etc. Actually, give or take, you can add or subtract filters which are necessary or which are unnecessary from the baseline of communication system for your own purpose. But mostly this system block diagram works from uh, uh, a case number one to case omega. Yeah, bandpass filter here. Yeah, bandpass filter is positioned here. As I already mentioned before, yeah, bandpass filter, that is a transmission coefficient which tops or has its maximum at the target passband. Uh, Out of the target passband, this and this, these are called stop bands. This is called bandpass filter. Likewise, low pass filter is uh, the guy which has the passband for the lower frequency. For the higher frequency, uh, it has tendency to suppress the signal. So it doesn't want the signals from the upper frequency or high frequency. That is a low pass filter. Um, on, uh, uh, on the contrary to that, high pass filter suppresses the lower frequency. Meanwhile, higher frequency signals are accepted. So this is the pass band in the high pass filter. Bandstop filter is if you flip bandpass filter, this is a bandstop filter. Bandstop filter is a target frequency band which in which the signals are desired to be suppressed. This is a stop band. Uh, except this valley, but there are two summits, right? These are pass bands in bandstop filter. Bandpass filter and bandstop filter using the resonators. But sometimes bandpass filters and bandstop filters are made the mixture of low pass filter and high pass filter. But what there are some limitations uh, when you would like to increase the slope from the passband to the uh, stop band, without using resonators. That's why uh, sometimes you can bring the mixture of low pass filter and high pass filter for generating band pass filtering and band stop filtering. But when you have good resonators, you can generate a good band pass filtering as well as band stop filtering. This function, a functional block diagram, is also familiar to you. This one is a simpler version, but you can add duplexer here. Duplexer distinguishes the path, path of the transmission and that of the reception using one antenna which has a large bandwidth which handles TX and RX frequency bands. You use one antenna for TX and RX or upper and uplink and downlink. Yeah, there are two paths. One path is a path of the transmission and the other is path of the reception. So duplexer is an extended version of filter. So I really like uh, designs of duplexer or multiplexers. Um, as always, my students and research staff are working very hard on developing good resonators, good filters, and good multiplexers. Duplexers are uh, a very attractive topic to you because sometimes people would like to use switches to um, distinguish the paths of a transmission line and uh, reception, but synchronization is the most important thing. And if there's a what little even little error in synchronization to switch or so to select one out of the two paths, TX and RX, but there's accumulated error in phase. What that causes a huge problem. So I prefer passive components instead of using the switches such as active components at the position of the gate of RF signal. Yeah, and you, as was mentioned with this block diagram, you see the positions or yeah, the relationships with their neighbors, yeah, of the bandpass filters. And I developed when I was working for a state-run research institute in Korea. I developed transponders for two satellites. These satellites are working well uh, in the space now. They bridge the gap between the ground via space to another part of the ground, like that. Um, yeah, this picture comes from my old research note. I am blocking the parts I didn't develop, but the other guys were developed by myself and with assistance of my junior researcher there. Um, Yeah, you see definitely the positions of the passive components, including antennas. This is an antenna. You can change the parabolic reflector antenna to something else if you pursue designs and implementation of a communication system for mobile communication. You don't have to use the parabolic reflector, but to send and receive the radio frequency signal over tens of thousands of kilometers. Mostly what that is the distance of satellite communication. We inevitably have high gain antennas and also high power handling structures. That's why uh, um, what, along with the planar or PCB-based structures, you will see waveguide-based structures, which are very good at or apt to the fields of high power or remote uh, uh, communication systems. And as you see here, antenna and the feed antenna, this antenna system or radiating element uh, should work over a wide band. Why? It also, this system block diagram of my satellite, Koreasat number 5, there there are two paths. As was mentioned earlier, two paths are TX path and reception path. So antenna is shared with the paths. But for the reception path or path of the RX, you see a coupler and input filter, and the input filter which accepts the radio frequency of a wideband, and it goes and it should be divided to different channels. This is called the input multiplexer or a demultiplexer. Demultiplexer means that's a channel splitter. At the end, right before the feed assembly, such as a horn antenna or high power antenna feeding structure, it is connected to the end of output multiplexer, which is called the OMUX. This is a channel combiner. So channel splitter and channel combiner, both of them use very good um, channel filters or filters. So there's a high level of complexity or difficulty in designing channel filters for or bandpass filters with the very narrow uh, uh, bandwidths or small fractional bandwidths um, are required. So channel splitter and channel uh, combiner. This is called multiplexer, and this is called multiplexer too. These are passive components. That's why we call these reciprocal structures. So uh, well, you can switch the roles from roles between output multiplexer and the input multiplexer or demultiplexer. I'm showing you some examples from my previous work, metamaterial filters. Recently, you can see an available a paper, technical paper um, available on the internet, which introduces very compact metamaterial waveguide structures, not just was SIW or substrate integrated waveguide structure. It's a real waveguide, metallic, hollow metallic waveguide. It uses it doesn't cheat on uh, uh, what using different flanges or non-standard flanges. My uh, metamaterial waveguide uh, filters use standard flanges, so there's no glitch or hurdle for my filters combined with to be combined with the standard input and output cables and adapters. You will see. But here, way before, years before the introduction of waveguide metamaterial filters, I developed a planar uh, structure of a CRLH or metamaterial filters. Um, the frequencies I was interested in were very low or much lower than uh, the other researchers pursue. Uh, the reason why I needed the CRLH or new types of filter designs for UHF or VHF or sometimes HF, those frequency bands are notorious for being so low compared to 2.4 gigahertz or frequency above 1 gigahertz. What people needed real small filters for real low frequency bands. So that's why I took the challenge and I could came up with I could come up with the good filters. What if you get a track of the this, filter papers on filters I developed, you can see what I mean. Passband, 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 new types of things. Uh, I think many people were inspired by the prototypes of the CRLH filters because um, most CRH early days CRLH or filter people showed what no big difference from the classic filters. Why? They're most of their filters were not real zeroth or resonators or negative net resonators, but I could prove why my filters are compliant with the names or the definitions of the composite right and left handedness. As you see, without the use of a low pass filter, stop band itself is very wide. Why? By using the zeroth order resonator, I can make my filters very small, but more importantly, I could suppress spurious frequency components after the passband, right? Of without the use of the low pass filter. So the reason is zeroth order resonance. Yeah, zero times n. N means the nth harmonic. Ideally or theoretically, harmonic doesn't occur like this, as you see. But this point and this point, these are the real. Why? The self-resonance resonances occur from some certain blocks of the filters, but these blocks are already small. and the level of suppression is already high. So uh, the guys who had to buy my ideas and who had to pay for uh, my filters, yeah, they uh, gave me a good review. Yeah, these filters, which do not require low pass filter, uh, at uh, at the foot of or the uh, uh, at the wake of the output parts of these filters. So they found out it's very interesting and working well, and also wideband. What that was a kind of a taboo. People thought zero throttle resonators and their filters are uh, uh, restricted in having a wideband or in generating the required bandwidth, but I could break the rule they set like this. And as I mentioned uh, at the bottom, as the bottom says, Tata Group's Radio Astronomy Institute, um, its name is NCRA TIFR, yeah, Tata Institute for Fundamental Research, yeah, Pune, India. Yeah, one researcher adopted my filters. As you see, you can make a comparison between my filter and his filter. Frequencies are a little different, but the uh, aims and purposes were exactly the same. And as you see, the geometry, by generating the good uh, and small resonators, uh, I could make a very good roll up. And he would use that idea to develop his filter. Though he curl the ending parts of the shunted L's, but the idea is the same. So you can refer to this paper, and if you, like him, need what advice or comments or cooperation from me to work on very low frequency but small filters, well, you it's a dial away. Yeah, filter design method without optimization. I'm going to get it unfolded. You already learned the basics or in microwave engineering 101 when you are given specs or user requirements, you decide whether it is category LPF, category HPF, category BPF, and category BSF. Yeah, the most of the baselines for filter designs are mathematics. Mathematics you can use the rational functions which have denominators and numerators, Hurwitz polynomials, kinds of things. All they are mathematics. So if you're geared for working on mathematical derivation, actually half is done. Yeah, and after mathematics, you take it to circuits. But circuits, though that is right in between, or it has two aspects, mathematics and reality. There, you oftentimes go back and forth between the stage of mathematics and that of realization. Lopez filter prototype is something familiar to you, right? Before taking um, uh, uh, what taking to the next step, taking the next step on a bandpass filter, what you do is low pass filter type prototype. Low pass filter prototype means the frequency is not an absolute value. That is omega. Omega, the capital letter omega means the normalized frequency, as you see. So this is starting point. if you want to have, if you want to have uh, 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 a bandpass filter or bandstop filter, first you should check the your low pass filter prototype. Yeah, omega over omega C. Omega C is the cutoff frequency of the low pass filter. In the normalized frequency, omega C becomes one, right? One, like this. Yeah, normalization and bandpass filter and frequency transformation changes low pass filter prototype to bandpass filter according to these formulae. So as you retrospect what was going on in your microwave engineering, a class of microwave engineering 101, you remember that is the frequency transformation. Yeah, this is a bandpass filter, and yeah, this will become yeah bandpass filter, and S21 is the transmission coefficient. But this is insertion method that directly takes it to the transfer function. Transfer function at the beginning, it is not complex value. It is the magnitude. User requirements come to you as the magnitude. They say amplitude, but I beg to differ. Um, that is the magnitude of transfer function, especially transfer function itself. No, that is the square. Square. That means power. S21 is very similar to, or it is the level of electric field, sometimes magnetic field, but electric field or voltage or current. But square, what is the square of voltage? What is square of current? Or what is square of the magnitude of electric field? That is power. So starting point is the power. So deliver power to load Y. They user requirements coming from a system developer or the guys who runs the service, they just give you from the standpoint of power like this. So it is a huge task. You should melt the user requirements in terms of the power to complex transfer function. That's your role. Insertion method tells you how you can handle that. Yeah, Kn is the function. This they say this is insertion and epsilon, but this doesn't mean permittivity. This is a kind of a controlling coefficient. Yeah, um, and as one as I already told you, the definition and this definition is matched with the mathematical form, and you want to know this k sub n square, this function. Still, this function is what everything is real, not complex, because this is power. So how can we find or extract the complex value from this real value? That's your job. Yeah, and S11 square is this is also a reflected power. This is a inserted or transmitted power, right? So mathematically, you can express this. Yeah, Kn is looking like this, but Kn, what coincidentally seems like the behavior of S21 square, even though as Kn is here. When Kn is getting large, Kn is getting large, what S21 becomes, sorry, it's just a kind of flipping image or mirror image of a Kn with reference to the omega axis. So here you think of this kind of a flipped mirror image is the something you can imagine. That is what you can imagine as the transmission. Yeah. Kn becomes large, S21 becomes smaller, and Kn becomes small, like zero. then S21 becomes what? Large, the maximum. So it's a kind of a mirror image between them. Yeah. S21 is like this. Yeah, this is what I mentioned. But this is a Hermit polynomial. There's a parallel function, they say. But at the end of the day, this will be synthesized, the combination or configuration of a LNC network. Yeah, here S21 and S11 is also uh, the flipping or mirroring effect. When S21 is maximum, S11 becomes the minimum, and vice versa. And Kn, luckily, Kn can be the polynomials well known to microwave engineering community uh, under the name of maximally flat. Maximally flat, this is the Butterworth or maximally flat or binomial function. And equirable or equalable, what either will be fine. Chebyshev function is the green curve. So k sub n square, uh, there are two curves. Uh, either both of them come from the mathematical descriptions or expressions. Chebyshev is this. So what you can uh, get a glimpse, which has the very sharp and a Roloff. Butterworth is for the same order. Chebyshev gives you a benefit. Why? With the limited number of resonators, yeah, order here means resonator. Resonator is the big, is either the series of LC or shunt of LC. LC makes a pole. So order is related to the number of the yeah number of resonators or the number of poles. So here you see with the same order for the same order compared to Butterworth, Chebyshev, even though it has ripple inside the normalized passband bandwidth, yeah, it gives the benefit. What? As you see, it has a better under skirt effect. So that's your choice. If you want to make the normalized passband block very flat, you will choose the Butterworth type. This is the Butterworth expression. It is a omega to the 2n, uh, and kn squared becomes Chebyshev uh, square if you want to have a better Roloff effect. So there are tables, but rather than Chebyshev, you can remind yourself of the tables, and um, with reference to the 1.1, 1.1 means the cutoff frequency, the position of the cutoff frequency, normalized frequency. Right after that, you can see this is a attenuation level. Attenuation is the inverse of the pass or transmission. So you can invert these curves from what you have now to uh, the opposite side. Then you think that is the transmission. So you can imagine n is equal to 1. It is very slow. The slope is very slow, but the slope is very fast at n is equal to 10. N means the order of the filter. Lopez filter prototype doesn't have combinations of LC. G1, G2, G3, they are not found to be at this stage L or C. We do not know. They are not resonators. They are just L or C. So here, if you want to have a what there, is not combined with the C. This is not combined with L like that. So G1, G3, G2, yeah, they according to the configuration you can choose. Yeah, pi type. Sorry, it is a T type or pi type. going with how you can get it started. If you want to make the problem is solved in terms of the input impedance, then uh, series inductance comes first. But these do not have the units at this stage. But sooner or later, you will see these coefficients or numbers will go with the units. This is Henry's or Farads like that. And if you want to have, yeah, you can compare, say, for example, n equal 3 between Butterworth and Chebyshev, n equal 3, when omega becomes 3 or when omega hits 3, you can see attenuation level 30, right? When you have Butterworth of order 3, this curve, you choose this curve. When omega hits 3, let me go a little smaller than 30, right? Yeah, it is a little above 30. So when the order of the filter is low, actually it is hard to distinguish the Butterworth better or Chebyshev better. But when you increase the order of the filters, then you can see the difference. And scaling, yeah, that is a frequency transformation. When you start with the low-pass filter prototype, you will choose to make it as a low-pass filter or high-pass filter, band-pass filter, and band-stop filter. These are the elements coming from G or LC as G, K coming from these tables LPF, then you will what get the normalized frequency back to the right one by dividing omega c like this. And yeah, these formulae were already introduced in the textbook, so you can check that out again. Impedance scaling. Impedance scaling means you also well, not only frequency was normalized, but also uh, the power supply, the or standard reference impedance or resonator was also set to be one. That means what normalization of the uh, resistance and the normalization of the uh, admittance. So you can check that out. For for us to make a bandpass filter, yeah, the shunt to C here, shunt to C or G1, shunt to G1 becomes shunt resonator, and the shunt series L here, series L becomes series LC. Yeah, these are resonators, right? Yeah. Uh, But mathematically, these resonators at the beginning, mathematically, are said to have the same resonance. But when you take it to the real implementation, then we need inverter like this. Then these resonators become to have different frequencies slightly by the addition or insertion of coupling coefficient. Coupling coefficients are expressed as J inverter and K inverter. Um, yeah, these are resonators, right? These are resonators. These resonators are something uh, much different from the ideal one. Why? Yeah, for one body, it has two different widths, right? So well, there's a perturbation. You cannot use a very what just plain rectangle. That should change like this. Why? Coupling area and non-coupling area for one resonator. The coupling makes the resonator resonate at the desired frequency. They are shifted above and below the target frequency, then you will uh, control and change this one, the gap as the coupling coefficient. The coupling coefficient and this coupling coefficient, actually we need one coupling coefficient between the two resonators. Say for example, yeah, you can eliminate this or you can eliminate this one between the two resonators, one, two, and input and output or input and output ports. Yeah, port coupling also is expressed as J inverter. Inverters uh, uh, inverters are known to have phase shift of 90 degrees, as you see. Yeah, actually, what there are a lot to come for the as the rest of classic filter design methods, but what you can refer to good textbooks written by um, uh, there are many filter gurus. You can check how the rest of the design methods, classic design methods, are going. Yeah. Uh, but just a way we jump from classic filter designs to uh, advanced or what improved filter design with the help of numerical optimization. Yeah, it is very bold. Yeah, this method is very bold. The classic filter designs starting from mathematics, but optimization method sometimes starts design lets the designs of filters starting with just configuration or matrix like this configuration you want to implement the filter with, right? Based on. So these values are all are variables or unknown, set to be unknown. And using genetic algorithm or with deep learning methods, you can find the these values which satisfy the cost function or criteria of your optimization technique. Like this too. This is a planar structure. This is a waveguide structure, comb line filter, which is commonly used in mobile communication area. Yeah, let me tap into genetic algorithm. The bolts and nuts about genetic algorithm can be found in good textbooks, but actually here I'm going to briefly talk about what it is. A genetic algorithm that mimics the principle of a generation making or producing another generation, right? So they use chromosome, and chromosome consists of genes, and this is called one individual, and individuals get together and they make a population like that. Gene or genes are bits. So these are mathematics, not optimization technique. But the reason I am introducing these mathematics, what these were really calculated and used for realizing my filters in the past. So, what and it's fun to see the differences between Chebyshev filter and elliptic filter response. This is a filter response of a elliptic integral filter for the fourth order, the same order as you see, the skirt is much better in elliptic integral filter. So yeah, you can try to find the unknowns LNC of the configuration of the filter you want to design. You can handle uh, uh, the findings of unknowns, the coefficients. Actually, you can see coefficients, right? Coefficients of complex transformation-based filter design to coupling coefficients. Coupling coefficients directly tells you what values of the coupling coefficients you need from resonator to resonator, from input to output port. So I am telling you, you can take uh, uh, one out of different approaches or perspectives. Yeah, configuration based like this, or yeah, transfer function doesn't tell you the configuration uh, explicitly, but inside you can get it. But a coupling coefficient also tells you some kind of configuration very directly to you. So the second, the third. So coupling coefficient, uh, coefficients are set to uh, let set to be unknowns, and they are part of the optimization technique. And especially if you need this kind of configuration, which is called canonical coupling, that means zero is the source and uh, nine is the output port. So 1, 2, 3, 4, 5, 6, 7, 8. These numbers mean the numbers of resonators. So resonator one all the way down to eight. So from one to two, actually this is called what sequential coupling. Sequential. The way it flows, it is called a sequential coupling. So between points or nodes are resonators. These are coupling coefficients. You will give M1 to here, and M23 here, and M34 here. Especially these dashed lines are called cross-coupling uh, paths. These cross-coupling paths, um, it this jumps. This line is the bridge between resonator 1 and resonator 8. If you want this configuration, or mostly what you start the coupling matrix-based filter design, start with canonical coupling, then going through matrix rotation, you will try to reach the final configuration you would like to have, like this. But we want to skip the process of matrix rotation. Matrix rotation is a kind of tedious, and sometimes it's uh, what really time consuming. But for specific topologies or configurations, the procedures which coupling coefficients are targeted to be eliminated, or what the elimination causes generation of unwanted coupling. That unwanted coupling should be at the next stage should be eliminated, but the removal of that unwanted coupling also causes the generation of another unwanted coupling. It goes on and on. It is called rotation, matrix rotation. But I wanted to skip that. So there, you just give the numbers here like this. The eighth order inline coupling, that was adopted in the design of my waveguide filters for satellites. Yeah, so you can use transfer function, you can use the coupling coefficient, you can use the configuration directly as the unknowns found or figured out by the um, optimization techniques. Yeah, this tells you similarity transform or matrix rotation. Um, it's a very interesting topic, but I'm not going to tell you what the details of this. But what in linear algebra, there's the field similarity transform. So when using this, the eigenvalues are still kept the same from beginning to the end of similarity transform, several procedures, but you should not change the eigenvalues. Eigenvalues there mean the poles, positions of the poles should be the same, but uh, the uh, uh, the matrix itself changes. Why? M12 goes away and M23 goes up, appears, and like this. But eigenvalues should be the same, as I mentioned before. Yeah. And specs are like these. When you are given these specs, uh, what you should think of is what uh, the uh, transmitted power first. But transmitted power is a real value which doesn't give you the details of information on circuits. To find the circuits or values of the circuits, actually you need complex transfer function. And I published several papers dealing with optimization methods helping the filter designs. Yeah, eighth order filter for Ka band satellite communication back then. And this is the what I made after realizing the filter response like this, and that was adopted in Korea Sat number 5. And this is the comparative study uh, showing the what mathematical and uh, the response frequency response of the realized filter. And we went further to have a better roll off or skirt performance. Yeah, and a lower order, fourth order filters, but a lower order compared to the higher order for this filter. This higher order filter is used as the channel filter for channel splitter, but in channel combiner, we need lower order filters like this. So there are one, two, three. There are three uh, uh, filters that are combined in the output multiplexer. And you can also deal with the what n channel OMUX, then uh, like what 6 or 8 output uh, multiplexer, then you should uh, uh, but extend this idea to come up with filter designs like that. Yeah. We've been all the way till this time. Yeah, conclusions are very simple. If you want to give channel selectivity to wireless communication system you are involved in developing, you need filters, right? Not only giving, providing channel selectivity, but also uh, making the wireless communication system or its quality good, you need to suppress unwanted